I'll give her. All right, so if you look at the top, the word radius you should have been familiar with before yesterday. You obviously have been dealing with the radius of a circle. I don't know when we start talking about circles in your math lives, but that's something that you would have been familiar with. And then yesterday, probably a new word would have been a chord. So all the things today deal with the idea of a radius and a chord, and then how those are related to each other. So quick little recap. If we look at this figure here, this is your radius. It's always got to extend from the center out to the circle. And then a chord has two endpoints that are on the circle, and then they're just connected to each other. So when we start talking about radius chords relationship, this is a radius, this is our chord, okay? There's some theorems then. The first thing you're gonna deal with a lot today, whenever we start talking about the distance from the center of a circle to a chord, let me go to the graph here so we can kind of talk about what this means. So here is obviously the center of your circle. We don't need to talk too much about that. If I want to know the distance from here to this chord, I can take a lot of steps to get to the chord. I can do it there. I can do it there. I can go straight across. A lot of different ways that I can get to this chord. If you are ever asked, though, to find the distance from the center to the chord, the one that we want to take is the one that makes the perpendicular segment to that chord. So when we look at these here, the one that's going to be defining, and we're going to do this a lot today, the distance is the one that's perpendicular to the chord. So when we start talking about the distance that the center is from a chord, it is the one that goes directly there at a 90-degree angle, okay? All right, so that's that first statement up here, so we can understand that. And then we have a few theorems that we'll work with. The first theorem is if a radius or part of a radius is perpendicular to a chord, so that's what we have set up here. Here is our radius, or part of a radius, depending if we continue. It is perpendicular because of this 90-degree angle to this chord. All right, so that's this first statement. If that is the case, then it bisects the chord. So an old word we haven't used now in a couple of months, but bisect means it cuts in half. So it's going to cut the chord directly in half. So what we did back when we were doing all of these, that means this segment here and this segment here are congruent. The little tick marks indicate that those are congruent segments. So ultimately, you don't need to write the numbers in, but if this was a 6, then we would know for a fact that this was a 6. It gets cut right in half. What you're going to fill in here, though, are the segments that are congruent. So what's congruent is the segment drawn from E to C. So we're going to write EC with the little segment symbol above it. That's where this first tick mark is at, and that would be congruent to the segment that I have marked right here, which would be the segment drawn from E to B. All right, so that's our first one. If our radius and chord are perpendicular to each other, the chord is getting cut in half. All right, the other one is just kind of the converse of that. And by that, I mean, this says if a radius or part of a radius bisects the chord. So if we know that this radius bisects this chord, then we would know that it is perpendicular. So it's kind of a give and take. If one is true, then the other has to be true. All right, largely it's the same exact idea. If we know these are getting bisected, then this has to be a 90-degree angle. All right, that's what this one is saying. So here is either the radius or part of our radius. It is bisecting the chord. So this would be our chord. Because we know that that is bisecting the chord, that then guarantees us that this angle right there is for sure a 90-degree angle. All right, so this is perpendicular. All right, so really those theorems go hand in hand. One is just the converse of the other. And then the third one, and we'll do some of these, the perpendicular bisect of a chord must pass through the center. So that's what this is doing right here. It's perpendicular and it's bisecting the chord. The only way that could possibly happen is if it goes through the center of that circle, okay? So those are some of our theorems. We're now going to use those to answer these questions. So go to example number 1. You were told that you have circle O. So here is O is the center. A circle is always named by the center of it. In this case, it's an O. You were told that if I went from A to O, this length right here is 5. Then you were told that if you went from D to B, so if we go from right here to here, that length is a 2. So find OC, OD, CD. The first two I would hope are nice. I would hope we could all get those. And then if you can get CD, that would be great. And CD is a little harder, but nothing really crazy new. Okay, so do those real quick. See if we can come up with those. Again, the first two should be nice, I hope. Not a lot of work you need to do. And then CD is the one that requires a little bit of work, but let's see if anybody can come up with that. A lot of people with the first two. That's good. Greek goddess. The math, still thinking a little bit. Processing.
Oh, we're using that weird triangle thing. Sin and
I like the beginning of that statement. We're using the weird triangle sound. But you said the wrong triangle. Weird triangle sound.
oh yeah, I just
Need somebody to CD so you can walk us through it here. Last period, there were a couple that.
He said all of them are shaped into the Idaho. So the other side is.
Right. We don't. That's we don't. It's actually something we did a long time ago.
oh,
You can't because they don't. It's really nice. You should not need to use so much, but we are going to use some of the right triangle. Right, Sage?
We're back to that.
What? Oh, there we go. There we go. There we go. Maria has it, right, Maria?
What?
All right, let's go through this, and then Hannah's going to walk us through here in a second, the third one. So, Haley, what'd you get for OC, Haley? Good. And why did you say that this is OC right here? How'd you know this was 5? What is it? Good. This is also the radius, right? So if you were given that the radius right here was 5, wouldn't any radius I draw into this circle, don't they all have to be 5? All right. So obviously we don't have these down here, but OC is just a different radius. So this has to have a length of 5 as well. Okay. All right. What did you get for OD, Haley? Good. She got 3 for OD. How'd you come up with that? Good. She did 5 minus 2 because isn't this what I'm highlighting in black? Isn't that just another radius? So that has to be 5. But you were given a little bit of it to be 2. So the remaining part to make sure that we end up with 5 needs to be a 3. Okay. Those are the two that are nice. Not a lot of computing. You don't really have to think too much about those. So hopefully we were able to get those, or if you now see it, it makes some sense. OD or CD is a little trickier. But Jackson asked, do we have to do the weird triangle things from before our long break from last week? And the answer to that is yes. But there's a lot of weird right triangle things that we did before break. Hannah, what is the weird Pythagorean, what is the weird right triangle thing that we have to do? I know, right? Can't mess it up now. What did you say, though? Good. And what's the Pythagorean theorem? What is it?
3 squared plus b squared equals 5 squared.
Okay, let's do this first. So just in general, remember this guy, Pythagorean theorem, a squared plus b squared equals c squared. Don't we now, what I have highlighted in yellow, don't we now just have a right triangle? And in that right triangle, don't we know 2 of the 3 sides? And if I know 2 of the 3 sides, this is how we find the third side if it's a right triangle, just the Pythagorean theorem. The key with this is making sure we have the right C. What did you say C was, Hannah? Good. The 5 is opposite of that right angle, so that has to be the C. And then the 3, you can make either one of them. We'll make it A, and then we set this up. That gives us a route to figure out what our B is, that missing side. Okay. So we now, once you know that, most of us are pretty good with this when we've been doing this. We've done this a handful of times on and off throughout the whole year. We just now go through and solve this. Subtract your 9 over. We're going to get b squared is equal to 16. What did you get then, Hannah, for b? Good. Our b should end up being a 4. All right. It's a little old right triangle trig stuff there with the Pythagorean theorem. Okay. That thing. That was the weird right triangle stuff, Jackson. Okay, so now go to the next one. A lot of these, again, you got to kind of work your way through. It makes us think a little bit, which is good. It says, given that AB is 12, so this whole length right here from A to B, this whole thing is 12 units long, and that's a chord. If you remember, if we use that word, that's our chord. The radius of this circle is 10. So I, again, could go from the center, draw in any radius I want, and know that all of these are 10. Drawing them down here doesn't do you any good, so we don't want to be putting them down there. But any radius we draw in, the radius is going to be a 10. The question then asks, how far is the chord from the center? So this goes back to what we talked about at the beginning. The way we figure out the distance from the center to a chord is always the perpendicular segment from the center. So when we go back to that problem, what we want to do is draw from the center a segment that is perpendicular to this chord. So that should look something like this, so that it is perpendicular, forming a 90-degree angle. I can get my pen to work. There we go. The answer to the question is this guy right here. How far is the chord from the center? That is the length that goes from the center at a 90-degree angle to the chord. All right. Next thing, when this intersects this, let's go again, just so we know we're not making this up, where we're getting all this from. This says if a radius is perpendicular to a chord, then it bisects the chord. So let's go back to our current problem. Our radius is perpendicular, so it's going to bisect this chord. So what that means is this full 12 just got cut in half. This length here is 6, and this length here is 6. All right. All right, final piece of information that we haven't sketched in yet is our radius is 10. So again, I drew some in down here. That wouldn't do us any good. I am going to draw a radius from the center to point B. Because if I do that, I now know that this is a 10. And then if this was new to us, since it's the first time we've done a real problem here in a week, now we should hopefully now see what we saw in that last one. Don't we now have a right triangle again? And we know 2 of the 3 sides. And we are asking you for the 3rd side. So now the Pythagorean theorem should be a little fresher in our minds. We are again going to go through this little process here. Just again, make sure we know which one is your C. The C is the hypotenuse. So that is the side opposite of the 90-degree angle, which is 10. All right, that has to be your C. And then from there, you can let 6 be the A, and then you're looking for that 3rd side. All right. Okay, so it's 36 plus b squared equals 100. Subtract over that 36. We get rid of squares with square roots. And our answer is 8. All right, got that? Makes sense? Okay. Next problem then. Try that one. Let me, without any prompting, see if it's very, very similar. Same theorems are in play here. So see if we can work our way through this one now, kind of understanding how we've done those previous couple. All right. so this is one of the things when we always talk about the distance from the center to a chord is always the perpendicular segment from the center up to it. So when this says the chord is 15 units from the center, here's the chord, here's the center, it's always that perpendicular segment. So this here has to be a 15. So when we start talking about the chord is 15 units from the center, here's your chord, here's your center, that perpendicular segment right here has all the and what you're looking for is we're looking for so if it's 15, you get it, you get a nice number. It's a nice number. Should be, like I told first period, some of your ages. Roddy is 8 years old.
I'm not 8.
Maria's 8 years old.
No. Wait, what?
Hannah was 8, Sage was 8.
So 16. Yeah, because 8 times 8. What? 8 plus 8 is 6.
The radius is 17. So that's a
Next is 6.
Did you figure it out yet, Riley?
Yeah, it's 16. I think 6.
All right, good. If you're getting 16, you did it right. Okay, if you got 16, then that's pretty good. All right. Let's put this together. Sounds like a lot of us are getting there. If you got 8, you kind of did it right. There's just that little extra step in making sure that we answer the question that's being asked. The first thing you want to be careful of is this phrase right here. When it says the chord is 15 units from the center, here is your chord. Here is your center. The distance between those is always that perpendicular segment in between them when we go directly there. So that 15 is alluding to this guy right there. That is the distance from the center to the chord, okay? The next one's pretty self-explanatory. The radius is 17, and like we've done in the first few, we want to create a triangle out of this. So I'm going to draw the 17 over here. And then what we've now created is a right triangle. So now for the third time, you've got the Pythagorean theorem. I'm going to be looking for this value right here. So I'm going to do a squared plus b squared equals c squared. So I have x squared. The c has to be that 17. And then 15 squared is either the a or the b. All right. So as walking around, most of us had that part of it. So we square each of those, subtract that 225 over, so that we get x squared is equal to 64. And when we now solve that with square roots, you get x to be an 8. So if we go here, we now know that this length right here is an 8. And as we're doing all these geometry topics, revisiting all of these, make sure you answer the question. We want to know the length of the chord. The chord is this full length. And what we said is if our segment is perpendicular to the chord, then it's cutting it in half. So if this part of it is 8, that means this part of it is also 8. And then that full length is the 16 that people were getting. Okay. So definitely makes us think a little bit, especially when you got to kind of draw your own. In this case, we had to kind of create our own. 4, you definitely need to create your own. So last one before we get a couple new little theorems on the back page. Do number 4. See what you think about that guy. I would draw it. Yes, I would strongly suggest drawing it in. If you think you can visualize it in your head without drawing it in, feel free. But I think it would be a little risky. Also, should be a nice number. If you get a nice number, decent chance you got it right. That's not a nice number here, huh? Think about what a radius is. Does it a radius that start at the center and go all the way out? Yeah, does this start at the center and go all the way out? And the question is, they asking find the distance from the center. That's the second. Is it S? Is it this over radius right here? That's your root. That's the radius. Correct. What was it? Yeah, that's right. You know. You do. Oh, do you not do the square root? Is that your issue? And then turn it sideways, you get see all these other options now. And then you do that. All right. I would definitely draw it in. Yours could look different than mine because somebody said it. I didn't necessarily catch who said it, but someone had said the chords can go anywhere. So you really could have put this any place. I'm going to draw it at the top of the circle since that's sort of where all these other ones were. So I'm going to draw my chord in right here. That chord is called PQ, and we know that that guy is 10 units long. We then have a radius. So if I go to the center of this, we have a radius that is 13. I'll draw that in a moment. And then the question is asking you find the distance from the center of the circle to the chord. That is always found by going directly there at a 90-degree angle. So that's the answer to the question. That's what we're trying to find, is that distance from the center to the chord, that 90-degree angle. All right. And then our radius is 13. That's how we're going to create that right triangle. Here is this right triangle. And then again, if we're going to use one of our little theorems here, if this segment is perpendicular to the chord, it also bisects our chord. So if this whole thing was a 10, that means this 10 got split in half. Half of it goes here, half of it goes right there. Those are the values we now use to set up the Pythagorean theorem. Okay, so now we should have x squared plus that 5 squared equals 13 squared. All right, and then walking around those who are doing the Pythagorean theorem, we're pretty good with this, not an issue. All right, subtract your 25 over. And again, you get a nice number here of 144. And then that should have been 12, which a lot of people were getting, which is good. Okay. No doubling that one. This is the length that we want, just that one segment length. All right. Okay, so that's those. Next one real quick on the back, couple quick little theorems, which again are kind of the same. We'll say one and the other is just the converse of that. So this says if two chords are equidistant from the center of a circle. So here's this chord, here is this chord. If they are equidistant, which means this segment here and this segment here are the same lengths, then we can conclude that the chords are congruent. All right, so these guys have to be congruent to each other. So if they are equidistant, so if both of these distances are the same, 3 and 3, then we know the chords they intersect are also congruent. Okay. The other one is largely the exact opposite. If two chords are congruent, so now if I tell you that these two chords are congruent, then we know they are equidistant from the center. Okay, then these have to be the same. So basically, if these are the same, then the chords are congruent. Or if the chords we know are congruent, then their distances are congruent. Okay, one and the same. All right, so go to this problem. Actually, let's fill this one in here. So in this theorem number 2, let's put this in. If AB is congruent to CD, then that is telling us that these two distances are also the same. So the first distance is x to O. The second distance is O to Y. Those also have to be congruent. Okay, so if the chords are congruent, their distance from the center are also congruent, and vice versa. All right, and then just one little problem to show this. So it says if AB is congruent to CD, so it's saying that these two chords are congruent to each other. So this chord and this chord are congruent. On our theorems, what that means, so real quick before we read anything else, since those two chords are congruent, that means that the distance from the center of those is also congruent. So these two red segments have to be congruent to each other. That's what we can conclude if the chords are congruent themselves, okay? Then what I tell you then, OP is 12x minus A5. Well, OP is this segment right here. So I'm going to label this 12x minus A5. And then you were told that OQ, which is the other distance right here, this OQ segment is 4x plus 19. So if we understand that theorem, that means these have to be equivalent to each other. So for the first time today, but not uncommon when we've done all these geometry ideas, we know that those two segments are equal. So that's what you're going to do. You're going to set them equal to each other. You then have a quick little equation that you're going to solve. Okay, we can all solve these equations. So we'll subtract that 4x over. Add your 5 over. Then just make sure you answer the question. X equals 3 is not our answer, correct? All right, we needed that. But make sure you're answering the question. The question is asking us how long is OP? What OP you were told is defined as is 12x minus a 5 right here. So the length of OP is that expression, but with a 3 substituted in for it. Okay, so OP is 36 minus a 5. It has a length of 31. All right. Try to keep all these straight. A lot of theorems coming at you here over the next few days. A lot of things to kind of get clouded in your head. Those are just a handful of those. Okay. So hopefully today, not too bad. Okay. Okay, and then we'll see how this goes. I'm a little worried for these.